Christina from Cornell University, and exploiting neighborhood interference. Thank you.
Thanks so much for the organizers for putting this together. I'm really excited to be here, and today I hope to tell you something of a very different, about a very different domain of problems I've been really excited about. So today I'll be talking about some work in causal inference in the presence of network interference. And my goal is to give you guys a flavor of what kind of the problems are out here, and hopefully get your interest as well to see if there's a lot of interesting questions. So to start off, we'll start with a motivating example. Suppose you work for a social media platform such as LinkedIn, and you want to evaluate a new algorithm for ranking items on your newsfeed. So one thing you might do is run a randomized control trial. So these companies are running randomized experimentation at scale all the time. So what you can do is you randomly assign a fraction of your users to have this new algorithm, where they may see a different experience on the newsfeed, and everyone else gets the status quo. And then you compare the performance on some metric, for example, user engagement, between the set of users assigned to the treatment group versus set of individuals. So that's a very common thing that is done, but the issue on a setting like this where there are complex networks is that the individual's behavior on social media platform actually have influence on each other. So say I was assigned to the control group, but my friends were assigned to the treatment group, and it could be that my friends' user engagement increases because they have a better product, and that increased engagement drives additional articles to my newsfeed. So even though I was placed in the control group, the measurement you have on my user engagement is actually not the same as if I was really in a control environment, right? So because of this network, now we call this network interference because this network is kind of now interfering with your ability to measure the outcome under treatment or control. So let me start with just setting up what's the broad problem setup that we'll look at today. So say here we want to evaluate the effect of some proposed treatment versus control on a fixed population of size n, which is connected via some network. And we'll use y to denote a potential outcomes function that specifies takes as input a vector of the treatment assignments. So it's every individual assigned to treatment or control, so it's 0, 1 variable, and there's n individuals. So it maps from this vector of a binary vector of length n to outcomes on that n users. So again, it specifies all hypothetical outcomes. If my treatment configuration was this vector, what would be the outcome, the configuration outcomes? And the causal estimate, the thing that we're going to want to estimate, is the difference between the average outcomes under the event where everyone is fully put in treatment or fully put in control. So here, it's just the average amongst all individuals of their outcome. Under the bold phase 1 is everyone treated, minus bold phase 0, everyone control. And the challenge is that we only can run a single experiment, right? So I run a single experiment, and then I want to, from that experiment, figure out how to estimate this total treatment effect. But that experiment itself is neither going to be all ones or all zeros, right? So I'm going to randomly generate a vector z, evaluate my outcomes y on that vector z, and then I want to figure out how to estimate this quantity here. And furthermore, there's an additional constraint that the treatment you're allowed to assign during the experiment is often budgeted. So here we're going to use p to denote the fraction of individuals assigned to treatment. And you should think of it as, let's say LinkedIn right there, if you propose a new algorithm, no matter how good you think it is, they still want to be cautious. They don't know what ramifications, unexpected ramifications there might be. So they say, okay, you can run an experiment on at most 5% of your users. That's already a large percent. But then p would be 0.05, right? So here, think of running an experiment where this vector z is only allowed to have a 0.05 fraction of ones, but you want to estimate this quantity. And the key assumption we'll use today is neighborhood interference. And in contrast, the classical work in causal inference often starts with a very strong assumption called stable unit treatment value assumption. And this is an assumption that posits that an individual's outcome only depends on the individual's own treatment. And so that allows you to reduce the potential outcomes. This is the potential outcome of individual I to only be a function on its own treatment assignment, so that it's only a function of a single binary variable. So this is obviously too restrictive for us. So we will look at an assumption called neighborhood interference, in which I posit that an individual's outcome only depends on the treatment of its neighbor. So here, script n denotes the neighborhood of node I. And so the potential outcomes of individual I under two vectors Z and Z prime are going to be exactly the same as long as the assignment to its neighborhood is the same. It also means that you can reduce the complexity of your potential outcomes function to only depend on a binary vector of length to the number, the size of the neighborhood. And furthermore, we're going to stay with the randomized experiment setting where these treatments, so this vector Z is going to be assigned randomly. So think of Z being drawn from a distribution, and you are the experimenter, so you can actually construct a distribution. I'll say that the other kind of very interesting space of work that we're not going to touch today is what if I actually have observational data? In observational data, you'll need to think about other types of assumptions on this vector Z, but it may not necessarily be randomly assigned. But we'll stick with the random setting, and when I say randomized design, it refers to the distribution of the treatment vectors. And I'll use so the superscript observed to denote the observation for unit I, and it's simply going to be the potential outcome for the applied vector, the applied treatment vectors. So let me show you what happens in a typical A/B testing setting. You take your individual, every individual I, you randomly assign them to treatment or control, let's say with, 50-50 or perhaps a different fraction. And then for individuals assigned to treatment, you get to observe their outcome under treatment. Individuals assigned to control, you observe the outcome under control. Again, this notation here already assumes that we have this assumption that's only a function of whether I was assigned to treatment or control. And then you can see that the total treatment effect is just the average difference between, again, a fully treated or fully control, and the difference in means estimator. So just taking the difference between the mean of the outcomes under the group of individuals assigned to treatment minus the average outcomes under individuals assigned to control is clearly a good estimate for this, but it does heavily rely on the randomization. It also heavily relies on this assumption. So in contrast, in the network interference setting, we're going to now be in a setting where the outcome of individual I depends on the treatment assignment of its entire neighborhood. The thing that we want to estimate, again, is the difference between average outcomes under a setting where everyone assigns treatment or everyone assigned to control. And the thing that you actually measure, if I do what we call the standard A/B test, if I randomly assign an individual to treatment or control, the thing I get a measurement of is the potential outcome of this individual under what happened to be that treatment configuration of this neighborhood. So in particular, this treatment configuration, if this vector Z of my neighborhood, some are treated and some are not treated, right? It's not clear how this measurement even relates to either of these two quantities in my estimate. And that's actually the simplest way to explain what's the challenge of causal inference under network interference is that you have a whole bunch of measurements that you just don't know what to do about, or what to do with. So it's very easy to see. You can construct all kinds of examples that if you just do a difference in means estimator, you can get a significant bias. And so the question today will be, how do we actually use data to collect from a very simple A/B test to estimate the total treatment effect under interference? And so I'm not going to talk too much about graphical models in this talk, but I thought maybe I'll take a moment here to pause and try to connect a little bit to connect a little bit to the problem we're looking at to what the graphical model would be. So imagine here I have these treatment variables v1 to zn. They're binary variables, and this distribution I can construct. So think of this as under my own control. So I can construct some distribution pz where this joint distribution is sample, right? So we're actually going to stick with a much simplest setting where, in fact, each of these z's are going to be independent Bernoullis. But you can think of there's more, really you're the experimenter, you can do whatever you want with it. And then you have your measurements, y1, y2, all the way to yn. And so every individual's outcome depends on their own treatment, but it also depends on treatment of others in the network. So here's function this. Okay, and think of this set here to be the neighborhood of individual I, right? And you should think this edge connectivity is the graph that's given to you. You can think of the graph as either being given to you or maybe you don't know it. we're good, for the purpose of the talk, we're mostly going to be in a setting where we know the graph. So we know this graph, we can construct this, and the thing is, the challenge is that we only get, let's say, a single observation. And when I say a single observation, I only can run one experiment. So I get a single sample from PZ. I get to observe all of these y1 to yn. These are deterministic functions of the z's, but I don't know what the functions are. And the thing I want to estimate is quantity. So the thing that makes it hard is that you clearly cannot fully identify the model because I only get one measurement. But the thing that I'm trying to estimate is also really simple. I'm just estimating a single scalable quantity. But I do have a constraint that I didn't write here, but this distribution PZ, think of it to be only constrained on vector z, whose L1 is small, right? So I have a budget. So it has a support limited or something like this, right? So I can construct distribution on vectors that have limited support. I get a single observation, and I want to estimate this quantity, but I'm only estimating something. Okay.
So I'm guessing you don't have any other assumptions, such as monotonicity, if you would increase the P, or look at my neighborhood. If I change some of the zeros to ones, that outcome behaves.
Yeah, so that's a great question. In fact, I'll talk about it in a moment. We will put assumptions, and I'll mention it. So yeah, this is a connection to graphical models, but we're not really going to use it all that much. But I do think there's interesting questions of thinking about, when you're in a regime where you don't have so much data to identify the model, but the thing that I want to estimate is actually really low dimensional. How do I think about what is possible and how should I do it? So let me tell you a little bit about what has been done in the literature. There's really two components that are involved in designing any experiment. First of all, you want to decide the randomized design. So what's this distribution PZ? And then second of all, you want to construct the estimate. So given my data, how do I actually construct an estimate of this quantity I want? And largely they fall into these two buckets. The folks that look at randomized design, they essentially look at how do you exploit the graph structure by constructing randomized designs that are based on clusters, cluster randomized designs, and use that to get really nice stuff. But the estimator they use is fairly standard. The second approach essentially looks at how do I impose structure on the potential outcomes model so that I can reduce it to regression. And I want to go into the literature a little bit more in detail just to build out that picture. Here I'm going to put all the literature on two axes. So think of the x-axis as representing the assumptions on your model, the potential outcomes model. The y-axis assumptions on your graph, right? So if I don't make any assumptions on the model or any assumptions on the graph, the first vanilla thing I might try is using what's called the Horvitz-Thompson estimator on a Bernoulli design. So Bernoulli design means that each one of these variables is a Bernoulli random variable that's independent. And Horvitz-Thompson estimator is as following. This one is a very simple to parse. It's an average between the observed outcomes amongst two groups. So this group one is all individuals for which themselves and their neighborhood are assigned to treatment, divided by the probability of that event, minus the individuals who themselves and their neighbors are assigned to control, divided by the probability of that event. So it's very straightforward. You can see, just taking the expectation of it, that indeed an expectation is the quantity we want. When you have a Bernoulli design specifically, these probabilities are really easy to compute. They're just products of these. So each pj is the probability that individual j is assigned to treatment. So if you ask, so this is clearly unbiased, what's the variance of this estimator? It looks like this, or at least the upper bound, a loose upper bound of it. You can easily show it's just this quantity here. Think of y max as just we're going to look at bounded potential outcomes functions. D is the degree of the graph. P is a fraction. So think of all of these individual PJ are equal to P. And the thing you want to pay attention to is in the denominator, you have n times P to the D. And the expensive part is the exponential cost in the degree. And that comes from naturally here that the probability of individual being assigned, its whole neighborhood being assigned to treatment is P to the D. So it's kind of unavoidable if you use this. I mean, this is more or less a type variance as well.
Christina, is D the average degree or the max degree or?
Let's say this is time for a deregular graph. So, yeah. I mean, if it's upper bound, you can clearly bound it by the max degree. I think it's a good question, like if you have different degree distribution, what's the right quantity that should pop up? So what you can say is, well, what if I had a really nice graph that consisted of disconnected subcommunities? This is a setting called partial interference or multiple networks. Then clearly you could just say, well, let me just treat each one of these subcommunities as a single unit, and I randomize jointly over them. So this entire cluster is fully assigned to treatment or fully assigned to control, and then you have to use the Horvitz-Thompson estimator, so that we're not innovating on the estimator here. And it's easy to show that basically you can get a variance that scales with 1 over C times P, where C is a number of clusters. And it's natural because now your number of units you're randomizing over is only C rather than N. So it works if you have a lot of really teeny clusters, but it doesn't work if you have only a few clusters. There's a really beautiful set of literature in this space, which anyways, if you haven't read the paper, it's really beautiful. But you look at like a general graph and say, well, why don't I construct clusters? So here, for example, I can choose individuals that form a 3 net, and then assign everyone else to their closest cluster center. So I construct clusters in this way. There's other ways to construct clusters. And then I jointly randomize over these clusters. Again, everyone in the cluster is either assigned to fully treatment or fully control. And you can imagine, like, even these cluster centers themselves can be randomly selected. And so in this setting, you can actually get much nicer variance bounds that scale only like 1 over n times p, and they have only polynomial dependence on the degree, and a polynomial dependence on what's called the restricted growth parameter. This kappa constrains how fast the neighborhood size can grow. So even though your 1 hop neighborhood is size D, how much your neighborhood size, your 2 hop, 3 hop neighborhood can be amplified by is at most kappa. So these are, I actually find this literature very, very nice. But the limiting part is that sometimes you're kind of constrained to experimentation platforms that don't support cluster randomized designs. You need a lot of engineers to overhaul your experimentation platform to be able to actually run these kind of randomized designs. And so it's still useful to think about what can you do without complex, what can you do if you're not able to implement complex designs. So the other axis, people naturally think about how do you impose structure on the model. The simplest model you should think of is obviously linear. We start with linear always. So imagine if my potential output function y is a linear functional of this feature phi, and phi can be any, so think of phi as a feature that captures everything that is relevant about the treatment assignment of your neighborhood. And in practice, really all the empirical studies, they use this assumption, and they use phi to be the fraction of treated neighbors or the number of treated neighbors. So if my potential outcomes function is linear in the number of my treated neighbors or in the fraction of treated neighbors, I just fit a line. It's important to note this alpha, beta, and gamma, the linear coefficients are shared across all units. And also that the usual guarantees you get from doing OLS does require that this delta I which captures all the heterogeneity, how much an individual's outcome can deviate away from the linear model, that has to be independent from these phis. So in particular, suppose I had 2 different linear models for low degree individuals and high degree individuals. It would break that assumption, because if phi is the fraction of treated neighbors, that's something that is correlated with the degree of the individual, and thus phi will be correlated with delta as well. So you do have to be careful, make sure your model is actually the correct model in some sense. And you can get behavior that looks kind of like what's called unobserved confounders, even though you're in a randomized experiment setting. So it's very interesting questions here too. So you can clearly extend that to other kinds of parametric models, or even where now I just think about other function classes, and you can reduce as well to various forms of regression.
So how do you determine what's the correct model?
That's the problem. So that is the problem. You can't. It's very hard to determine what's the correct model, and it's not just the correct model in terms of the F, but also the correct set of features to use in your model. And if you choose the wrong set of features or insufficient, then also all guarantees go up. So yeah.
I guess so on the right hand column, what would be the ideal dependence on N, P, D, and
Okay, here. So here the variance, so here you would expect 1 over n. P doesn't play as strong of a role unless your degree is really high. So basically, the main what would I think governing the variance, right? It's I have one data point for every individual n, and what I want is I want to make sure that the spread is large enough in this phi if it's a fraction of treated individuals. If I have a high degree, then the fraction of treated individuals will concentrate, and that will make the variance higher because we'll only have a few points around concentrated around here. But so I think what will play a role will be I guess that will govern the variance. But it's not as clear because these ones really come from the fact that you're just taking an empirical average, and the number of samples you have is p times that. Here you're not really, so the number of points in some sense is really all of n, but then you're governed by how much spread you can get in the features. But to my knowledge, I don't think people have looked at too much on how to optimize. So that's a great question. Okay, so the starting point of our work was asking, what's this question mark, right? Here, all of these settings, you reduce it to regression. But regression is a setting where you fully identify the model, and it's much stronger than us estimating just the total treatment effect, right? Now, is there a setting here where we can estimate the total treatment effect, but you can't reduce it to regression? And there's some way to understand the complexity, what is the complexity of a model class, right? That is kind of suitable. So what we suggest is a class of models that is parameterized by what we'll call this parameter beta, which governs the order of interactions of the model. And we'll look at we'll propose an estimator under Bernoulli randomized design that gets this variance. And the way to interpret it is that we have polynomial dependence on d instead of exponential, but we have exponential dependence on beta. And this d to the 2 beta is actually not tight. When you take beta close to so in the fully general setting, beta is equal to d, the graph degree, then you will recover the Orbis constant estimator. It will actually become this estimator itself. But specifically when beta is small, then this will be nice. And in the linear model setting, beta is just 1. Okay, so that's what we'll mostly talk about today. I just want to tell you a little bit about some other work we have, looking at all of the other solutions require knowledge of the network itself. And so what can you do if you don't have knowledge of the network? What we look at in these sets of papers is looking at how if you have a richer measurements of your outcomes, so in particular if I'm allowed to run my experiment over multiple time stages and I get multiple measurements, just multiple measurements itself is able to relax the requirement on knowledge of networks so that I can actually get a meaningful estimator without having any knowledge of the network. And then in another set of work, we're looking at if you have extremely rich measurement of outcomes, think of a time series data, then you can actually estimate closer to individual causal effects. Okay. So let me tell you a little bit about the model that we are going to work with. And to start with, I'll show you how we came up with this set of models. And the first starting point is really nothing at all. It's just saying that I can write my potential outcomes function as a sum over all subsets of the neighborhood of, AIT is going to be my outcome under if this set was treated and everyone was not treated. So T is the set that is treated, everyone in the complement of T is in control. And then because this my assignments are binary, I can write this indicator function as a polynomial. And then you can see, once I write it as a polynomial this way, that actually the degree of this polynomial is bounded by the degree of the graph. So I'm going to change basis. So we're going to change it to the monomial basis. So in a moment. So here is the version I wrote above. I'm just going to rearrange it and write it in the monomial basis. And so we'll, for the rest of the talk, use this form. So I'm just going to say that without loss of generality, any potential output function can be written as a polynomial of these treatment variables, where the degree of the polynomial is bounded by the degree of the graph. So once we know that it's a polynomial, there's kind of a natural way to measure complexity of polynomials, and that's the polynomial degree. And so really for the rest of the talk, that's what we're going to be thinking about is how do you actually, is this polynomial degree of the potential outcomes function meaningful in some way? And what we're going to say is meaningful is that we can actually construct an estimator in which the degree of the polynomial degree is the quantity that we're going to refer to as beta, that degree of interactions, and we'll show that indeed we can come up with upper and lower bounds on the variance and the mean squared error that really depend on this polynomial degree. So and again the idea is then to show that models with lower polynomial degree are indeed actually simpler to estimate. Any questions about this?
Is there some complementary lower bound that says that in full generality you cannot do any better than highest degree polynomial, degree highest, which is the degree of the connectivity of the graph? So there's something like that.
When you say cannot do better, what do you, sorry, say it again.
There is no design G that gives you.
Okay, sorry, I should pause. I should roll back. I realized I had an assumption in my mind I didn't tell you yet. So the result I'm gonna tell you about today is that under Bernoulli design, so if I assume that all of these were independently randomized, then we're gonna give both a lower bound that no estimator can achieve mean squared error above like 1 over n to the p to the beta, n times p to the beta, so that's that the beta kind of governs that, and an estimator whose variance is scales kind of like n times p to the beta in the denominator, except actually these factors that are polynomial indeed. But the thing that we have not yet, we are currently exploring, but we don't have tight results on, is the question of now if I allow myself to play around with the randomized design P, what's the right optimal kind of thing you can gain from both exploiting low degree in the polynomial and the potential function, as well as like the graph structure. So since we are going to be sticking with Bernoulli design, the graph structure does end up playing a very small role, other than upper bounding the polynomial degree. Yeah. Right. So you see here. So if I have a degree beta polynomial potential output model, the number of parameter is going to scale as n times e to the beta, because you have to specify all of these coefficients for sets of size up to beta and out of set of size d. And we call this, so I introduced this as a low degree polynomial. I do want to remind you that these variables z that's polynomial in are binary. So that's why we also call it the low order interactions, because when you think of polynomial, it's not really this Goodwin function, right? It's a low degree binary or polynomial binary variable. So really you should think of it as that there's lower interactions in how the network interference arises. Okay, so assuming this low degree is equivalent to kind of saying that, here we had a previous slide showing how you go from the outcomes to the monomial basis, and so it does imply something about the outcomes themselves as well. And so in particular, when beta is equal to 1, the linear model. It's actually equivalent to what was previously looked at as the joint assumptions of additivity of main effects and interaction effects. So the beta equals 1 model was one that was looked at before. And for arbitrary models, beta is going to be the maximum network degree. So in this way, you can think of when beta equals 1, you reduce to something like linear models. When beta equals the network degree, you can model any arbitrary potential outcomes. And so,
The linear model that you showed earlier also had the idiosyncratic nodes, right? You're also assuming some node-specific idiosyncratic noise here, or this is?
So here, actually, let me pause that and I'll show you on the next slide. So actually, here is what the model looks like in beta equals 1, if it's linear. If you have a linear assumption, essentially our model reduces to assuming that your potential outcome function is some baseline parameter, alpha I, plus the effect of yourself being treated on yourself, plus for every one of your neighbors that's treated, their effect on you. And what's different about the previous linear model is that these alpha I, CIK, they're all indexed by I. So I'm no longer, so the previous linear model, there was a single global alpha, beta, and gamma that was shared by all, and then this individual delta I was governing how much does an individual I deviate with from the linear model. Here, because all of these alpha I, CI, CIK are already all indexed by I, you don't need to add an extra deviation term, right? Like you can capture that all in alpha I if you want. So it kind of subsumes the previous ones. And you can show that this model actually does arise from assuming these two properties. So this additivity of main effect says that my potential outcome is equal to the potential outcome under fully control plus the difference between whether I'm treated or I'm not treated under fully control, plus the difference between my neighborhood treatment minus fully control. And the additivity is just saying the fact that you can actually compose these. And then the additivity of interaction is saying that, well, how does the treatment of neighborhoods decompose? You can decompose it individually over individual neighbors. And you can directly map this assumption to apply that form. And one other way you can visualize the model is this way. So you can think of the observed outcomes vector y to be a vector, your baseline vector alpha, plus the kind of network effects times whether or not each individual is treated. And you can visualize it on a graph this way, where on the nodes, I've written the weight of the node as the baseline parameter. The self edges are going to be the direct effect of myself being treated on myself, and the edge from like 6 to 3 is the effect of individual 6 being treated on individual 3. So if I treat individual 2, 5, 8, I color them red, and then I color all their outgoing edges red as well. And then when I take measurements, I sum over the weights of the incoming red edges plus the weight of the node itself. And so something that we like about the model is that you actually do allow arbitrary unit-specific coefficients, because all these coefficients are indexed by I. There's more parameters than measurements. There's only n measurements, but there's at least number of edges measured parameters. And it does generalize these linear models without the need for feature engineering, right? So you think of feature engineering here as kind of like here we're allowing these CIKs, these edge weights, to be fully personalized. And settings beyond beta equal 1 could arise, say, if I have a network that's partitioned into subcommunities, if the network effects are additive amongst the subcommunities, then the degree of the model is at most the size of the largest subcommunity. If I have some feature that is limited to only groups of size, let's say like a Hangouts room feature that is limited to groups of size more than 5, then the degree of these interactions can be only at most size 5 as well. If the outcome is a polynomial function of any linear combination, you also get some low degree polynomial. Or if the network only arises from pairwise or triangular interactions, that's where these lower stuff can happen. So I think this set of works, I'm mostly going to focus on the first one, but this set of works really looks at how do we exploit these low order interactions to design new estimators whose performance is actually characterized by this complexity measure, the polynomial degree. And today we'll talk about just the Bernoulli design setting, where it's the most classical experiment setup. But I did allude to earlier that if you have a richer experiment setting, which we call a staggered rollout design, if I'm actually, let's say I have a period of 5 days, on day 1 I treat at 2%, then 5%, then 10%, 20%, so I actually can take measurements at different treatment levels. Then you can actually get graph agnostic estimators as well. Okay, so let me just review what the inference task is, and we'll talk about the results mostly in the setting beta equals 1, and then I'll mention how it generalizes. So again, we're going to assume non-uniform Bernoulli design, so each individual is treated independently with probability p, or here they don't have to be uniform, so pj is the probability of treating individual j. You should think of treatments as acting on these outgoing edges, right? So if I treat individual 5, the outgoing edges are colored red. In this picture, it's as if I treat these individuals, this is the treatment vector, then it's as if I'm selecting these columns of the matrix. And what are my measurements? My measurements are on incoming edges, right? So my measurement here, so what do I measure? The outcome of this individual is its own node weight plus the sum of the incoming edges, which is the same as row sums. So I'm measuring row sums of highlighted columns plus this base. And the thing you want to estimate is the total treatment effect. In the beta equals 1 setting, the total treatment effect is the sum of is equivalent to estimating the sum of the weights on all the edges, excluding the self loops. So we want to exclude the self loops. Actually, no, sorry. I'm excluding the node weights. I'm not excluding the self loops. So that's good. I'm excluding the node weights, but we do want to estimate the self loops as well, because they are part of the network effect as well. But it's the same as estimating the sum of all the weights in this matrix here. Okay, so I'll pause here. Any questions about the task and the setup? So let me tell you about how we derived the estimator. Well, actually, this is not how we derived it, but it's in retrospect how we explain it. So suppose I focus on a single node I. The observation, right, of node I is a linear function. And let's start with a hypothetical setting that we hypothetically have samples from m independent replications of the experiment, so that I can have, like, here are my m replications. These are the unknown coefficients I want to estimate. These are the treatment assignments of my m replications. Then I could just run OLS. I probably don't even, well, yeah. It's even easier because I don't have a noise term. The number of covariants, and this setting would be the degree plus 1. And okay, so if I let y tilde is this vector, x is this matrix, w is this unknown vector I want to estimate, and z tilde is a single realization of one of those row vectors, then I can estimate this unknown weight vector using just OLS, and you can easily see that the true weight vector is just the expectation of this covariant matrix times the z tilde times the observation. And one thing to observe is that this matrix here is actually designed by us. The z tilde, it comes from the randomized design PZ, and so we construct it. We actually know this. We don't need to use samples to estimate it. The thing that we don't know is this y term. And furthermore, this is actually invertible because we're using a Bernoulli randomized design. So what you can do then is say, well, if I only have a single sample now, I don't have m multiplications anymore, I can construct an unbiased estimate for these coefficients just by replacing this expectation, the one I can't compute, with a single sample. And that's going to really be unbiased. Again, this matrix is a known function of your randomized design. And now the second thing to observe is that the thing I want to estimate, the total treatment effect, is a linear functional of these weight vectors W. So it's just, again, something like the sum of all these weights. And so if I have an unbiased estimate of this W hat, I can use it to construct an unbiased estimate of these total treatment effects, right? So I have a linear functional of my weights, and I construct a W hat, and I get an estimate of my total treatment effect this way. And it's useful again that the fact that I'm looking at an average treatment effect, and so this 1 over n of course is important. So even though a single estimate of W hat is not consistent, I'm just taking an average of them, and because the goal is a single scalar quantity that is actually normalized, then everything is okay as well. I should comment. One thing I should comment. Okay, so here, these W hats are actually correlated. So these across different i's, they are not independent, and that's because these W hat i's are a function of the treatment assignment of its neighborhood. So if I have I and I prime that share a neighborhood, the W hats are going to be correlated. So when you do the variance calculation, so I argued that this is unbiased. How you show the variance calculation, you have to be a little bit more careful, and argue that if you have a sparse graph, that they're even though they're not dependent, the dependence is okay. So this approach is not specific to total treatment effect. You can really use any linear estimand. You can estimate any linear estimand. You can imagine other designs beyond Bernoulli. You just need a good property on this quantity here. And if it's not invertible, you use the pseudo-inverse instead. And so this is actually an idea that was presented in a very different context as the pseudo-inverse estimator in sleep recommendation setting. And their setting was a little bit simpler in that their estimates that we had were actually independent. Alright, so I'll show you what the estimator looks like if I actually compute it out explicitly for the Bernoulli randomized design. So my expected matrix ZZ transpose looks like this. Right, I just have I'll get the spherical variance matrix. It's a very simple one because everything's independent. I can then invert it and then plug it into that form, and I get an estimator that looks like this. I'll put it in big in the next slide. So this estimator looks kind of interesting in that essentially what you're doing is you're taking average over all outcomes, but what do I multiply this outcome with? I multiply the outcome of individual I with the sum over all of its neighbors of some quantity that looks kind of like this inverse probability weighted quantity, right? But except for the weird thing, I think the sum is the thing that looks different. That doesn't show up in settings without network inference. You can show in this setting that when beta equals 1, you get this 1 over NP scaling and polynomial. And this estimator is similar to, I'll just put this reference here that it's actually an estimator that's very similar to another estimator that was in the literature as well, but kind of in a different context. So I'll just show you the kind of verification that is indeed unbiased. If I take, this is our estimator, I plug in the potential outcomes function. You can verify this unbiased very easily. You can notice first of all the expectation of this quantity is 0, and so by construction of these weights, and so that means that I zero out this component here that I don't want to involve. That's not in my estimand. And then if I multiply this sum of these weights by zi, then I get 1, because zi is independent from any other j that's not equal to I. And so you get the expectation of zi times zj, or zi times this is 0, but then when you multiply zi by its own term, you just pick out the first term. You get 1. And similarly, if I multiply it by zk for any one of these guys, I also get expectation of 1. So you can verify indeed that it is its expectation is what we want. So next I'll just tell you a little bit how you can extend it to general beta. Again, you can use the same approach and say I can focus on a single node, think about writing the linear functional of a set of covariates. Now these are a little bit more complex covariates, are functions of sets. I can run my hypothetical experiment to see that actually the thing I want to estimate this weights is a quantity that I know times a quantity I don't know, but I can get a single unbiased estimate for. And you can see that indeed verify the total treatment effect is still linear with respect to these unknown weights. You can construct an unbiased estimate of an unknown weight and then estimate the total treatment effect by aggregating all the estimates across the weights. And so if you plug it all through, you get this estimator. It's looks similar to the other one before, but now it has a sum over all subsets of size beta of the product of these weights over all individuals in that set. And you can run through the calculation to show us if they're biased. If you do the variance as a kind of calculation on it, you do get that the kind of important term in the denominator is n times p to the beta. And then we have a polynomial dependence on the degree. So we don't think this part is tight, but this part in the bottom is tight. If your constraint on the degree of the model is not actually constraining, in particular if it's larger than the graph degree, you actually recover the original Cornell-Thompson estimator. So it indeed kind of becomes fully general then, and you get what you expect. So as I alluded, you can actually construct a lower bound where if you look at a deregular graph, you have uniform treatment probabilities, and here there's a condition here to say that if your treatment probability is very small, so we're in the setting where p is small, then any estimate of the total treatment effect has to incur a mean squared error that scales as 1 over n times p to the beta. So indeed, that kind of verifies to us that this beta really is a meaningful notion of capturing the complexity of estimating the total treatment effect. And the construction is a simple one that is based on instances where you only put weights on sets of size exactly beta. So you say that for any set that has size exactly beta, either it's drawn from this model on the left or this model on the right, where this network effect is Gaussian with like either plus delta or minus delta scaled by the number of sets of that size. Okay, so I have a few minutes, so I thought maybe I'll just end by telling you a little bit about the key idea as well in this set of works. So the earlier slide I showed you, if I only have a single measurement, how do I do it? How do I do estimation under Bernoulli design? Now I'm going to tell you what happens if you have a more richer design. So suppose I have a staggered rollout design with treatment budget P. The treatments are administered or implemented over T stages. And what that means is that suppose it looks like this, where at stage 0, nobody's treated. Stage 1, these additional 2 people treated. Every time point, I add more people treated until at stage T, I have a P fraction treated. But the point now is I get to get measurements at each of these interim time points, and the question is, what does that do for me? So what you're able to do is choose a treatment schedule, and we're going to stick with the Bernoulli staggered rollout design. So condition on who was treated before, the new treatments are Bernoulli. And these staggered rollout, I did want to comment, they're already actually used in a lot of domains. And so the one slide kind of intuition is that actually, if you have this connection between the potential outcomes functions and polynomial models, you can actually reduce the estimation task to just polynomial interpolation. And the idea is, suppose I define a new polynomial f, a polynomial of p, the treatment function, and this function f of p is the expected average outcomes under the setting where I have Bernoulli p randomized design. And you can, plug in your potential outcomes function, compute the expectation, and see that it's indeed a degree beta polynomial in this parameter p. And now what the thing you want to estimate is the total treatment effect is just this function evaluated at 1, everyone treated, or this function evaluated at 0, everyone in control. And at stage t, you observe a noisy signal of f of pt. And so essentially, if you have enough measurements larger than the degree of the polynomial, then you get noisy estimates, right, of f of pt at t different points, and you want to estimate a beta degree polynomial. So, and then once you estimate your beta degree polynomial, you just estimate f of 1 minus f. So you can kind of run through that easily and show that you can. When we plugged in Lagrange interpolation, you can plug in really any. But for Lagrange interpolation, we kind of did the variance calculation and we got something like this. We don't know if this is tight, but it kind of has a similar flavor as the variance bound that we had in the first section. And the big aha or interesting thing I think is that the fact that you get multiple measurements, the staggered rollout design, not only does it make the intuition, it reduces the estimation time to something as simple as polynomial interpolation, but there's no part of the estimator where we use knowledge of the network. Because all we did was we fitted a polynomial to statistics which were just aggregate population-wide outcomes that did not use any network knowledge at all. I think this overall approach is not, it may not be specific to polynomial functions. The idea is maybe this potential outcomes function is actually some other function class that's a function of p and you get multiple measurements of it and you want to estimate it. It does require that this potential outcomes model is kind of fixed with respect to time so that when you take multiple measurements, the function itself doesn't change. So that's something that could be looked into to relax. And it doesn't utilize fine-grained measurements of the individuals, right? All we do is we aggregate the population-wide outcome and we fit a polynomial to that. And so it's interesting whether, can you do better by actually using the data in a more involved way. All right, I think I'll wrap it up here, and I'll just mention that I think some things I didn't talk about that we don't really know how to do is how do you actually choose this model complexity beta if you don't know it in advance? Can you optimize the randomized design along with the choice of estimator? That's something we started to look into, but it's still quite open. And can you do anything with observational data instead of just randomized designs?